Imagine that you have followed all the rules, designed a database that meets all the requirements of the third normal form, but it still breaks. That's exactly what happened to Raymond Boyce in the 1970s, which led to the development of Boyce-Codd Normal Form, short for BCNF. In this video, we are going to introduce you to the Boyce-Codd Normal Form, yet this video isn't just about BCNF. It's also about how one of the most elegant theories in databases turned out to have a subtle flaw, and how a young research scientist caught it. Before we get to the drama, let's quickly recall what the third normal form is trying to prevent. For a table to be in the third normal form, it needs to be in the first and the second normal forms first. What the third normal form specifically requires is that no non-key columns are transitively dependent on any candidate keys. For example, a violation of the third normal form may look like this. That's when you have a non-key column that's functionally dependent on another non-key column, which in turn depends on some key, like what you see here on the screen. To fix a table that violates the requirement of the third normal form, like this one, you need to move the columns in the transitive dependency to a different table, and the determinant will become the primary key of the new table. Additionally, you will keep all the columns that are directly dependent on the keys, the primary key or a candidate key in the old table. There would be typically a column that meets both of the two conditions and will be shared and placed in both tables, like what you see here in this example on the screen. The third normal form was developed by Edgar Codd in 1970. His work laid the foundation for nearly all modern database systems, for which he won a Turing Award. The development of the third normal form was detailed in his paper titled A Relational Model of Data for Large Shared Data Banks, published in 1970. After the paper was published, for 4 years, no one examined or challenged whether the third normal form definition was sufficiently rigorous. In 1974, a young scientist named Raymond Boyce was working through database design examples and noticed something odd. When two candidate keys share a column or they have an overlap, the third normal form doesn't always protect you from update or delete anomalies it is supposed to address. For example, think about a table named teacher course. It is a messed up design, of course, and probably won't make much sense to the real world. But it is useful enough theoretically. The table has two candidate keys, and both of them are composite keys. The first key uses two columns, teacher ID and course ID, while the second one uses course ID and room. The functional dependency in the table is between two columns, course ID and room. And the functional dependency states that course ID functionally determines room. This design is perfectly valid in the eyes of the third normal form, as all the columns belong to some candidate keys or primary key. So there's no non-key columns, thus no transitive dependency. However, if you ever try to populate the table with data, and then try to perform an update, such as updating the room where CS101 is told, you need to find all the rows where course ID is CS101 and then update all their corresponding room numbers. Otherwise, you will have an update anomaly. Remember, the functional dependency between course ID and room asks you to do this accordingly. So the third normal form is not strictly enough, especially the focus on the non-key columns. Theoretically speaking, you can have some rogue columns that are part of some key and still give you all the trouble of transitive dependencies. Actually, It doesn't have to be a transitive dependency at all, as you saw from this example. When a part of a key is functionally dependent on a part of another key, it is already bad enough to give you update or delete anomalies. To address such issues, Edgar and Raymond worked together to develop the Boyce-Codd Normal Form. It requires a table to be in the third normal form first. Beyond that, it also requires that every determinant in a table needs to be a candidate key, but nothing else. This new normal form successfully fixed the loophole discovered by Raymond. If a table is not in BCNF, you will fix this design by splitting it to more smaller tables based on the violating functional dependency. In the example that we visited, it's the course ID that functionally determines the room which violates BCNF, so we will split them to a different table, and make the determinant the primary key in the new table. The original table should only keep rows columns that are functionally determined by some candidate keys. Since course ID meets both conditions, it will be kept in both tables. That said, I need to confess that BCNF is rarely used in real world because it's very hard to find a table that violates only BCNF but not the third normal form. But BCNF is still valuable to database theories and is the foundation of the field. The best part of this lecture is not about BCNF or the loophole of the third normal form. It's about people. Edgar initially resisted the idea that his definition of the third normal form was incomplete, but he eventually embraced the correction. And when they successfully developed a new normal form that fixed the issue, Raymond's name came first in the name of this normal form. BCNF may be rare in practice, but it represents something very important and valuable, the pursuit of completeness even when the flaw is very rare. In this video, we started from the tiny loophole of the third normal form and explored how it was discovered and fixed, and ultimately led to the Boyce-Codd Normal Form. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain concepts. You can find the link to the book in the first comment.